Okay, so as said before, the old data here are the data prior to the new legislation. So the defined model here, function, there's of course a help page for it. I'll try to cover the essentials, but there are many more options that I won't cover. So k var, k being the number of variables in the state. So what is the dimensionality of the system? So in this case 7. You'll make an AR1 model and include an A and like 1. I will remove variables 1, 6, and 7. And then at first, just to compare with the original paper that was done, I would treat variables 2 through 5 as independent variables. So that means I will not fit a multivariate setting. So if I look at what is actually in here, I get an AR pattern, which is the first thing is always a unity matrix for the lag 0, and then I get the AR1 coefficient here. Notice that there's nothing for the year and nothing for the legislation parts out there as well. There are just a diagonal, 4 diagonal elements of 1s here to say I want a univariate. I want 4 univariate AR1 processes. Effectively, that's what I'm doing. For the moving average part, again we have a density matrix of full rank in the first, and then again a diagonal, a subdiagonal with 4 1s in here to say what it is that we have. And except for the unity leading part there, in all the other matrices here, a 1 means that there should be estimated a coefficient, a 0 means don't estimate anything. So I can change any of these 0s or 1s to something to the other value, and then I'll change the model structure. So usually just define the order. For here I can go in and pinpoint I want these particular coefficients to be estimated, yes or no. So there's a lot of freedom which you can use and misuse. To estimate this, you take the data, you say, do you want the mean values? You take the AR pattern, the moving average pattern, and then for now I won't plot anything or check. I'll just run it. The estimation is quite swift. And then if you don't want to see the unity matrix always, then there's a short form function to help you kind of get the output out that you want. So if it's short form of the AR coefficients gives you a full matrix. Again, it's a 7 by 7 matrix, but there are zeros everywhere where I said remove variables. There are just zeros out there, but they are there such that you can fairly easily compare models at a later point in time. If you kind of take things in and out, everything is at the same dimension. So you can say, yeah, well, that's handling too many numbers, but it's just, you can say, a little bit of extra bookkeeping that is done. And also the estimated MA part. I won't spend much time on this because this is just univariate models. For the second model, what is the difference is that the independent here, which was previously up here, set to true numbers 2 to 5. Oops. I give that a null now. If I estimate the model where I just take the AR and MA part from model 2, now I will also do a plot of the determinant. Then first looking at this out here, this is the convergence plot. Basically what you care about is that it levels out at the end. Or do you need to do more than 50 iterations? So there's an option where you can increase the number of iterations, but that you just want to care about that it's not doing some odd oscillation at the end. So this is the logarithm of the determinant of the residual covariance matrix. Does that stabilize? Yes or no? Nothing here is saying a good value, I mean, an appropriate value, is that a high value or a small value? That depends. We just want to have a fit. And a good fit is something that's converged. The difference here is now the model up here. If we look at that again, both for the AR and MA part, we have a 4x4 block matrix in here, indicating that we're going to estimate 16 MA coefficient and 16 AR coefficients up there. And you say, now we can just look at the values. We cannot, I mean, what does it mean right now? I won't spend much time because we're not done fitting the model. Just show you that we did actually estimate, in this case, 16 for each of these, plus a covariance matrix. So we estimated 48 parameters in this case, from 83 observations of a four-dimensional system. So you should keep in mind that the 83, you could say each value there has about 83 observations, but in total we have the 300 and some observations. So we're not fitting too much. Now, the question here was actually, is there a legislation effect? So the next thing, I will just take some more data in here where I include the legislation data. I will again do an AR1 model. Instead of removing, before I was removing variables 6 and 7 as well, now I change them to be regression variables in my input. And what you will see here is, if you do not define something for a variable, it means that they should be included in the ordinary sense. But let's just look at what we specify here. So the moving average, let's take the AR pattern first. We have the identity matrix first. And then we have this block here where we say that the suicide and homicides rates here, 2 columns of rows 2 through 5, depends on the same rates the year before, and it depends on the legislation the year before and the cumulative legislation as well. For the moving average part, we have the identity matrix, and we have again the 4x4 block. So basically that means there's no noise influencing the legislation effect, because those are to be treated as regression variables. They are only coming in and influencing the output, not anything else. The fit of the model is exactly the same thing. Done. You don't have to zoom in to see that this converges nicely. If we look at now the estimated parameters, we do get extra columns out there. We get 2 columns and 4 rows of extra values out here. And likewise for the moving average part, we have this expected structure, a 4x4 matrix. So here we estimated 8 parameters more than just before. So it's a quite big model. And now in a case like this, if I was doing this, well, I am, what would be the usual question? I have quite a large number of parameters. Are they all significant? So what we can get out is also from the marima object. I'll just look at the names of. There's a lot of different things that are in that object, and if we print it, what we've looked at so far are the estimates for the AR and MA part. But we also have some F statistics or some p-values. Let's just look at the F statistics here. For the AR part, ar.f values. I mean, again, there are zeros everywhere where we did not estimate anything. That's just a convention. It could have been anything out there, but it's just treated as zeros. But we do see that we have F statistics that are, say, 0.11 there. And if we look at the MA part, as I remember it, we even have an F statistic of 0.01. So what does it have to be, the F statistic, in order to be significant? Do you remember? What does it take for an F statistic to be indicating significance? Should it be large or small? Large, exactly. And now the next step is defining a threshold larger than something. The usual threshold, if you do a 5% level is, in this case, let's just look at it. Look at the quantile for the F distribution that corresponds to a 95%, no, got the order, yeah, 95% level. And then I forgot the order of the arguments here. We have 90. So 3.94 is a reasonable value in this case. Okay, but we can also use, as was said in written in the other report, if you use 2 as the threshold boundary, then it coincides with the AIC criteria. So for now, we'll just stick to something close to 2. So the next part here is including, essentially it's the same model definition, but did not have to make a new one here. I just copied all the code from the PDF. Actually, I did it for the previous version of the PDF. And then the difference is that I changed to have a penalty. Let's just start with a penalty of 1. It takes a little bit longer. Now I will want to look at this graph again, because now it looks a little bit different from before, right? Before, what you saw was there was an initial kind of swing and then it kind of leveled out. So what happens here is that it will take the first one-third of the iterations that are allowed to do, so the first 17, it will do just as before, trying to get in the right neighborhood. Then it will use step, each time removing the least significant variable that does not improve, such that the AIC is improved, as in lowered. It does that for a period of time, and every time it leaves out, every iteration it leaves out one variable if there's something that is not significant. What does that mean? It removes one parameter at every iteration, but it does not wait until it converges again. It just does it one step at a time. So it means that the F values that is being used are approximative. And then when it's done that for up to 1/3 of the time, at some point the step does not reduce anything further, so it will just stop, and then it will converge to the final model. So if we look at what happened, then you'll notice that now there are some zero coefficients here and there. I'll do this again in a moment. Look at the MA part here. You see that there are actually only, in this case, 1. There's nothing here. So nothing depends on what is the previous value of Y3 for the MA part. For the noise, it's just pure noise that goes in there. And then you have 2 here and 2 there. So it's actually a very simple MA1 part. If we look at the remaining F values, we will see that, I mean, everything that is less than 1 is set to 0. And actually, in this case, I remember I have checked that all the remaining values have values that are greater than 1. But if I change the penalty here to 2 and rerun, I get a similar graph. If I look at the AR coefficients here, everything here looks fine. You can see that only a few variables are actually left now. So we have 1, 2, 3, 4, 5, 6, 7 coefficients in the AR part, and for the moving average part, you also just have a few parameters left. Now, just to show you as an example, I'll do something that doesn't make too much sense, but I noticed that the smallest value here is 2.03. So I will try to increase the penalty to 2.1 just to show that it sometimes happens. That even though I set a cutoff value of 2.1, I end up with an F value that is less than that. The reason is that when you look at the convergence graph here, it is not allowed to converge before it chooses what to remove and what not to remove. So it will not remove this one because the F value of that is at the point in the step recursions is above 2.1. If you want to do something better, you can do this manually, or you can also automate it. Didn't I include that in this code? No. But basically, how to deal with this, you know that, at least I've said it. If you want to get rid of this particular value that is estimated here, what do you do?
Can you just remove the variable? It seems that the function is in the package.
You can remove that variable, but what you want to do is to say, you want to look at the marima for objects, you want to look at what is called the out MA pattern. So this is the pattern that these are the parameters that are estimated. So if I go in and fix this one here, change that to a 0, and use that as an input to a new model fit, we can just do it here. So I'll make a copy of this. And then I'll take coefficient, and now this is one of the things where you have to think a little bit. Which coefficient am I actually looking at? I'm looking at the last element there should be a 2. And then I want row 3 and column 2. That was a 1. I'll make that a 0. And then I will go up and copy the call to marima. I could give it another name, but what I will do now is, rather than using this pattern from, I will do more. I will also do it for the MA. Thank you. But what I will do is I'll take the marima pattern, the marima 4 fit, because I don't want to restart the whole thing. I will use the AR pattern that I ended up having, rather than starting back from scratch, because that is what corresponds to my new MA pattern. If I now run this model, you will see that it actually took the first 17 iterations and it was almost already converging. and it's not reducing the model any further in this case, because there was only this one particular one parameter that had to be done something to. And now I can of course look at the outcome of this. I'll call this B. And now you see that only a few parameters are actually left in here. So particular, the legislation effect only has an effect on the, and it has an immediate effect on the second and fourth variable. That, if you go back, no, sorry, and it's the first and third in the, you can say in the data. Let me just go back here, get back to where the data was. So it has an effect on the suicide by firearms and suicide by other means. That is what is directly affected, and suicide by other means, there's an immediate effect and then there's a trend following that. But now you can say it's only estimated based on 7 values after, so that trend is not that well defined, but it appears that there is one there that is significant, at least using this threshold that we chose to use. And we could of course also look at the remaining F values. For the AR part, we see that all these values are great. I think the smallest one is 4.62. So in this case, I mean, using a penalty of 2 or 3 point something, it gives the same model. And for the, what? Didn't I fix that to be not estimated? That was odd. It did change a little bit. Now it is not estimated. I forgot to run a line. That's always good. But you will see now that everything is significant, and also significant at a level where the choice of penalty does not matter, which will often be the case as long as you have a penalty somewhere. If things are really influential, they will be there no matter what. So the last step here is how to make predictions. Now I'll just take the entire data set, and there's a function called arma.forecast, and pretty much what it does is that you give it the full data set where you have NAs, you have rows for everywhere where you want to have the predictions stored as well. You say you're going to use the first 90 observations as my lead-in, so to speak, and I want to make a 10-step prediction from there. And I'm using this model. I will change to my new model. That gives me some forecasts. Here it's just specifying which model was used. Just a default print. So from here on, maybe you should just look at what is in that forecast. So we pretty much have the forecasts in here, and then we have the residuals from the model. We have the prediction variances. We have the averages, and we have what is the pattern that is used for the mean. So we calculate a mean value for every one of these, and also the average is calculated for every column in the data. Also for those that we said remove these. So there is one place here where it's kind of annoying that you also have a prediction error for the year. That is 667. You did not make a model for it. You can't, basically what happened was that you estimate the variance, and you have a model that is just a global mean value. So all of those where you remove it, it's there. So you can also compare with that. What does it actually, how does it improve the model if you include something for the year? I mean, we could make a trivial one that says make an individual model for the year, and it will say that the year is equal to 1 plus the last year. No variance, perfect fit. Doesn't make much sense, but it's just to say that it will actually, even though we said totally to remove everywhere else, but in these prediction variances, there are zeros out there, but here they're left in. So these are the prediction years, the last 10, and the actual part of the data that are predictions are the last 10 observations. Like this is just one of the variables, the second one, which is the second column, so that corresponds to the suicide by firearm, which is, you can say, the one we care about the most originally. Then we look at the prediction variances, and what we do there is to get the second row, second column, that element for all points in time. And then we just make the upper and lower limits. In this case, not using the standard value of 1.92, 96, but something different. I don't know if you remember by heart what this represents. Plus minus 1.645 standard deviations represents. You can think of that, I won't say it. You pick a value that represents something. What you should always declare when you write something is what is the coverage of the prediction interval that you make. Then I just column bind it, and we can just look at what are the values there, and we want to make a plot. Let's first plot the data. So these are all the observations. There's something odd here. Why does it drop that much? These are the, here comes the data. So those are the years. The first one was all my forecasts. So yeah, here we have all the forecasts plotted with a line, and here I plot the original data as points to use the same structure as been done in the PDF. And then for the prediction, I will just add a prediction interval. And if I want to look at the residuals, oh sorry, that's something different. Let's just take a look at this graph. Oops. Does this look reasonable? Maybe I should add an AB line. Now I went back one plot, so I should remove the current plot. Hopefully this works. That is where the legislation was put in place. So I mean, definitely here there is a downward trend. It may already have started before, but there's definitely, you can say, ups and downs over time just by random. We can say the variance here is maybe not unrealistic. The last plot was just looking at all the residuals in one plot. That's what we have. I think it's difficult to see here. So let me just increase the line width. Now you can see more of it at least. But I mean, it looks fairly random. The green line has more variance, but that's how it is. Okay, so this was the marima case. What I did not present, but that is in here in the PDF version of it, Here there were some plots of the predictions for all the variables. There are also, you can say, the usual what should you do about residual analysis. Of course, you can look at the residuals. You should also look at the autocorrelation of the residuals and partial autocorrelation function, a QQ plot, and other things. You can say that's the usual story. So I've chosen not to spend too much time on that. But of course, when you're doing a model, if you want to kind of say, is this a good model or not, that's something you ought to do.